So hello dear students. So today I'm going to give you a derivation of the Bethe Bloch formula. And if you remember earlier, in the earlier lectures, it was given that whenever some radiation is interacting with matter, then the transference of energy per unit length or the stopping power, which is called, it is given by this formula, which is known as Bethe Bloch formula. And I'm going to give you an elementary derivation of this formula today, based upon simple facts like the Rutherford scattering, etc. And so that you will have an idea on what factors does the stopping power depends upon. So what are the various parameters on which the stopping power depends upon? So what are the, like for example, velocity or the charge of the medium or the projectile, whatever all these parameters are there. So there is a dependence of the energy loss inside a medium because on those parameters. So you can get an idea about that if you know the formula, and so how it is derived, what is the physics behind it. I'll give you an idea about that in this particular section. So let us start. So what are the physical assumptions here? So let us talk about heavy charge particles which are traveling inside a medium. So here, heavy charge particle having mass m much greater than the mass of the electron. So what is happening is a heavy charge particle enters a medium, interacts with the electrons of that medium. The mass of the heavy charge particle is very large compared to the mass of the electron, and it has got a charge Ze. So the heavy charge particle is having an atomic number Z. The nucleus is having an atomic number Z. Simply straight line path, because the fact is what is happening, the charge is very heavy, so it does not deflect that much because the electron is very light. So compared to the mass of the electron, the heavy charge particle is very heavy, so it does not deflect in its path. So it is also of very high speed, which is relativistic, and electrons generally compared to the heavy charge particle are treated as if they are at rest with respect to the heavy charge particles. So basically you can say that electron is at rest and the charge particle is moving with a very high velocity. And the dominant energy loss in this case is ionization of the atomic electron. That is, if the heavy charge particle will lose energy. And how will it lose energy? It will lose energy because what will happen is the heavy charge particle is going to transfer its energy to the atom, and the atom would absorb this energy, and ionization of the atom will take place. So the loss in energy is the dominant process for the loss in energy is the ionization of the atomic electron. Okay. So if you know what is Rutherford's formula, so the transfer of energy E, delta E. So this energy transfer is basically calculated by the Rutherford formula, and it depends upon the charge of the incoming projectile and mass of the electron, the velocity of the incoming projectile, and the what is called as the impact parameter B. So this is an impact parameter B. So this quantity is called an impact parameter. And what is happening is what is B minimum? It is basically maximum transferable energy. So the B minimum is the smallest impact parameter possible, and that smallest impact parameter basically transfer maximum of energy. The maximum energy is transferred when the impact parameter is the minimum. So let us say if you have let us say some projectiles are coming like this in this direction, and you have a target here. So the atom is sitting here somewhere, and then so the projectile comes here and gets deflected in this direction. So this distance, the perpendicular distance from the atom, the distance of least approach d, this distance is the impact parameter. So for every particular particle that is coming out, the impact parameter is different. So it's the distance of closest approach, as you can say, so between the atom and the incoming projectile. So B minimum, when the incoming parameter or the impact parameter is the smallest, the transfer of energy is the largest. And what is B max? That is the maximum value that this impact parameter can obtain. This impact parameter would be when the energy transfer is maximum. So B maximum is the value for which the energy transfer is minimum. And what is the minimum energy transfer? Actually, what is happening is the minimum energy required for ionization is the minimum energy that the incoming projectile is going to transfer to the atom, because this much of energy is required. The excitation energy is required to excite the electron out of the atom. And before, if the energy is lower than that, then the atom will not absorb that energy. So simply stated, the energy that is required to ionize the atom, that much of energy would be which would be the mean excitation energy or potential I, and that would correspond to B max. So there are two values of B minimum and B max. I think you have understood. B minimum is the minimum impact parameter and B max is the maximum impact parameter. So let us go on next. So let us start. So we have a cylindrical shell. So let us start here. So let us say the radiations are coming out. Let me erase this. Okay. So let us say we have radiation that are coming out of this board. So the direction of the radiation is outside the board, and you have an atom here. So you have some atom here, and then let us draw a cylindrical shell around this atom. So we have a cylindrical shell around this atom. So this is an atom A, you can say, and the radiation all of them are coming in the forward direction. So let us talk about this shell. Now we are talking about this shell, and what is the area of the shell? The area of the shell is simply this distance, which is B, times dB, which is the thickness of the shell. Okay, so the thickness of the shell is dB, and B is the impact parameter or the distance of the atom with the incoming radiation, which is, for the time being, we are taking only the shell. The radiation is present inside the shell. So 2 pi B into dB would be the area of the shell, and the number would be this n would be the number of incoming particles per unit area, or the flux of particles. So let us say you multiply this and with the dz. Okay, so you get dn, the number of particles which are coming inside or outside in front of you from this shell. So from this shell, the incoming projectile is coming out. So the heavy charge particles are coming out from all the places, but let us consider this shell alone. And in this shell, the total number of particles dn would be n into 2 pi b dB dz, where dz would be simply the distance traveled by the incoming projectile in the forward direction. So the distance traveled by the incoming projectile is dz. But so when you divide this So we get from here, what you do is stopping power would be delta of E of B. E is a function of delta E is a function of B, as we have said, times dn, which is the number of particles in the shell, and we integrate it over the whole cylinder from B min to B max. So this would give us dE by dx. Simply dE by dx would be delta E into dn by dz. So you can say dz here. So simply stated, if you know what is dn by dz, then you integrate it dE by dx, you will get as integral of delta E of B dot dn by dz. And since you know earlier what is the dependence of, let us go back to the earlier formula for EB. So from the Rutherford scattering, the amount of energy transferred is inversely proportional to B square. So if you remember this, you can go forward and you will get, and when you integrate this delta E with dn, which is dn is n into 2 pi b dB, then you will get a logarithmic dependence, that is ln of B max over B min. So simply stated, because delta E of B has an inverse B square dependence and you multiply by B, then you get an inverse B dependence and you integrate it from B min to B max, then you get this kind of dependence ln B max over B min. So let us go forward. So now what is the maximum energy? So maximum energy would be, so let us say you have a heavy charge particle here. So you have a heavy charge particle which is having certain mass. I think we have skipped one slide here. Here, okay. So as I said earlier, what is W max? So you have a heavy charge particle which is going in this direction, and you have an electron here. So you have a particle P which is moving in this direction and striking the electron. So what is the maximum energy it can transfer? The maximum energy it can transfer is when the electron approaches this particle, it gets reflected back. So the direction of the momentum changes by 180 degrees. So when the direction of the momentum changes by 180 degrees, so what is the momentum of the electron in the frame of reference of the incoming projectile? So in the frame of reference of the incoming projectile, the velocity of the electron is v, and the mass of the electron is m e, and then you have a gamma factor. So this is the momentum. As you know, the relativistic momentum is given by this. So relativistic momentum is just gamma factor, where gamma, you know, is given by 1 over under root 1 minus v square by c square. So if this is gamma, then the relativistic momentum is gamma mev, and the maximum momentum transfer is 2 mev. So this is the P max. So the maximum momentum transfer as the electron approaches and gets reflected back is 2 mev. So the maximum energy W max would be P max square over 2 me, and when you calculate it, you will get W max is equal to 2 me c square beta square into gamma square, where beta, if you know what is beta, is just V by C. So simply stated, your W max is 2 MEC square beta square gamma square, and your W min is equal to I, which is the average or mean ionization potential. So ln B max over B min is just ln 2 MEC square beta square gamma square over I. So you get this dependence on the this various terms which are related to the stopping power. Additional relativistic term also appears, which is equal to minus beta square, and this appears if the particle's velocity is very high and is of the relativistic regime or the relativistic limit. At that point of time, we have to take the transfer of energy which is calculated by the scattering amplitude, and that scattering amplitude you have to do a relativistic calculation for it, and that relativistic calculation was first done by Mott. And the relativistic scattering formula is called, for a heavy charge particle which is interacting or which is scattered by an electron, the Mott formula, or it is called the Mott scattering. Oh, let me see. So you have an additional relativistic term. So you have all these terms here, and we are going to put them together here. So what we are going to do, we are going to put them together, and what we get is dE by dx, which is a stopping power. So this is the stopping power. And it depends upon all these factors here. So we put all these factors that we have calculated here, we get a dependence like this on a logarithmic dependence, and the other factors come because if you remember in Rutherford scattering you have different other factors also, like epsilon naught, and of course the number density was there, that came into picture when we calculated the total flux that is coming out of the shell. So all these factors, when you put them together, you get this formula. And the value of K given here is 0.307 MeV centimeter square per gram in CGS unit. And this formula, which is the Bethe Bloch formula for heavy charge particles, is valid for heavy charge particles, and it has got this dependence on the velocity of the incoming projectile, the mean ionization energy of the medium, and the other factors like the mass of the electron, etc. And also the Z, the charge of the incoming ion. That is also one of the parameters. So it depends upon all these things as Z square. So these kind of factors, they come up here. So you have, you can have a look on this formula, and let us now proceed from here. So a lot of corrections were proposed to the Bethe Bloch formula. One of the corrections that was proposed was the density effect. So what was the density effect? So basically when a heavy charge particle enters a medium, and if it is very fastly moving, it is relativistic, and that charge particle polarizes the medium, and in the process of polarization, the charges, the positive ions that shift or change or are displaced, what they do is they shield the total effective field of the incoming projectile, so that the interaction of the incoming projectile with the electron reduces. So you need to have a density effect or a density correction for that. Similarly, you have shell corrections. If the projectile is of very low velocity compared to the velocity of the electrons inside the atom, at that particular juncture, what happens is it spends a lot of time in the vicinity of the electrons, so it affects the inner shells also. Not just the shells which are responsible for the excitation of the medium atom, but other shells which are inner shells, those shells are also affected. So you have to have a shell correction for that also. Then you have Barkha's and Bloch correction. That is also a very important correction. You can say higher order in Z. So basically any kind of scattering cross section involves higher order in Z. So if you are talking about when you're talking about, let us say, scattering, so you have higher orders of correction, like for example, in the simple Taylor expansion of any particular integral. So in that case, what happens is you get higher orders of z. So there is a Born approximation which tells you about the scattering of some incoming particle with another particle, and that Born series has higher orders of z. So higher order corrections like z, you can say Z3 dependence, Z raised to power 3 dependence is also included in this particular formula, and it is called the Barkas and Bloch correction. So let us go back. So the final Bethe Bloch formula after corrections. So you have this logarithmic dependence which we have calculated earlier. Then you have the relativistic correction here, which is given by the Mott scattering formula, which is a correction of inside the Bloch equation itself. And then you have delta, which is the density correction, and other correction, which is the Barkas and Bloch correction. And we have already seen that maximum kinetic energy transferred is 2me c square beta square gamma square. So you can see, we can summarize all the results. Delta E, or the transfer of energy, is basically inversely proportional to b square, as we have already seen, and that was the result given by the classic equation of Rutherford. Then the stopping power is basically, when you integrate, you get to calculate the stopping power, then you get a logarithmic dependence over b, and it scales as z square by b square. The stopping power is proportional to z square and inversely proportional to beta square, that is inversely proportional to velocity of the incoming projectile, velocity of the square of the velocity of the incoming projectile, and the final formula includes both density and shell corrections.